So basically, chemistry is the study of the composition, structure, and properties of matter, the processes that matter undergoes, the energy changes that accompany these processes. That is your basic textbook definition of chemistry. And in a typical high school chemistry class, we look at that. And in looking at that, what we do is we try to look at that from the smallest particle of matter, and which is the atom, but really even the parts that make up the atom, up through to the phases of matter. And then in laboratory experiments, we look at these different topics in terms of reactions and interactions. Chemistry is broken down, like many of the sciences, into more specific branches. This class, whether you are in the honors class or in the general class, this class is basically a general or an introduction to chemistry. So we don't necessarily focus on any one branch or any one topic, but we try to give an overview of all the different aspects of chemistry. The first and maybe the biggest branch of chemistry is organic chemistry. And organic chemistry is going to be the study of carbon-containing compounds, or most carbon-containing compounds. Organic chemistry is really just a large, it cuts a large swath of the study of chemistry. When I was in college as a pre-med biology major, the two first chemistry classes I took were organic chemistry. That was 2 whole semesters of a 4-credit class, 8 credits of organic chemistry, fall and spring semester of my freshman year. And so organic chemistry is just a huge part of chemistry. We also look at inorganic chemistry, and that's just the opposite of organic, the study of non-organic substances. There are very often organic fragments bonded to metals, and we'll look at metals in inorganic chemistry. Those are called organometals or organometallics. My second year of college as a pre-med major, my next 2 chemistry classes were inorganic and quantitative analysis. You would do inorganic fall, and you do quantitative analysis spring, and those were also large classes. The labs were bigger in those classes, and as you move from inorganic into quantitative analysis, there's a lot more math and a lot more calculations. Those were 5-credit classes, 2 labs a week. So you can start to get hopefully a sense and a feel for how big this study is. We go on to physical chemistry, and it's looking at properties and changes of matter and their connection to energy. And we'll spend a good bit of time in class doing that and looking at that in terms of the labs that we do in particular. We also have analytical chemistry. I already talked about that. Analytical is kind of connected to the class that I took called quantitative analysis, and that's identifying components and composition of materials. And what we know we can do in the lab, basically based on the body of knowledge that we have, is we can break unknown materials down and learn things about those unknown materials, and based on what we learn and based on what we know, identify what the unknown materials are. Moving into biochemistry, when I was in college, biochemistry was a non-lab 3-credit class, and it's the study of substances and processes occurring in living things. So, what is the underlying chemical reactions and processes that are connected to life? Cellular respiration, photosynthesis, and much deeper than that as well. And that's what that study entails. And we look at what we call theoretical chemistry, and this is applying mathematics, and today not just mathematics in terms of hand calculations, but also using computers as we put the formulas in the computers to work through and understand the principles behind observed chemical behavior. And we can predict properties of new compounds. This gets into the idea and the concept of computer modeling. If we have some set of knowns and we've got equations, we can put this into the computer and let the computer model what a new compound would look like if that is a new compound that we are trying to synthesize for a particular use, process, manufacturing procedure, so on and so forth. Now, let's go through some more definitions here, guys. It's important for you to recognize that any scientific endeavor and really any academic pursuit is going to have what I would refer to, or what I would call, its own jargon. Jargon basically being a technical language, and so it's important that you know the language of what you're studying. Okay, so to discuss chemistry, we need to know what a chemical is, and a chemical is any substance that has a definite composition. So in a lot of ways, that very general and very accurate definition means that most things we know about and we come in contact with are chemicals. They have a chemical basis. Sucrose is sugar. It's a substance that has a definite composition. Water is a chemical. It's a substance that has a definite composition. Carbon dioxide is a chemical. It's a substance that has a definite composition. Chemicals go into making the laptop that you're probably using to listen to this lecture. Chemicals are what make up the ingredients of the air, the atmosphere, in the tabletop or the desk that your laptop is sitting on, and what the clothes are made out of that you're wearing right now. So we come in contact with chemicals more often than we think we probably do, and a common misconception at the high school level is to think that chemicals are the white powders or the liquids that come in the jars with labels that we use in the lab. But those just represent specific chemicals. Most of what we come in contact with on a daily basis is a chemical. Basic research is carried out for the sake of increasing knowledge. So in terms of chemistry and doing research, this is where we move into looking at things at a very fundamental, basic level where we don't have knowledge and we want to increase that knowledge. If we look in chemistry, we know that a reaction occurs, but we don't know why and we don't know how, so we're trying to figure that out. We have a substance and we don't know what it is, or it's a new substance, and we try to be able to identify the properties. And in chemistry, identifying the properties could be telling me, its color, or its luster, or identifying properties could be doing experiments to determine its density, or its specific heat, or those types of things. The discovery of Teflon would be an example of basic research. Okay, having this new substance, figuring out reactions and how these reactions create it and what the properties are, so on and so forth. Applied research is very different. Applied research is much more specific, and applied research is being done to solve a very particular problem. To try to develop new refrigerants. When we got to a point in our country when the CFCs, or the chlorofluorocarbons, were outlawed, the Freon was not legal to use in air conditioning systems anymore. It didn't mean that companies stopped manufacturing air conditioning. It didn't mean that companies stopped creating aerosol cans with propellants. What their R&D, their research and development divisions within those companies had to do was develop a new refrigerant that would work in the air conditioner, something that was not outlawed, something that had at least some of the same properties of Freon, or develop a new propellant that could go in the aerosol can that wasn't a chlorofluorocarbon. That is applied research. And this ultimately leads to technological development, where we have the production and use of products that improve our quality of life. But that production and use of those products comes from the general and then the applied research that allows us to then move those new substances into manufacturing. So computers would be an example of technological development that come out of chemical research. Catalytic converters in cars would be another example. And a catalytic converter in car is something that actually creates a chamber for more chemical reactions and processes to take place. Having biodegradable materials that we can use in processes and plants and places. And so what this means is when we look at basic research and define it, and applied research and define it, and technological development, we can see that usually there's a lot of overlap, and very often one will lead to the other. Now, the top 8 chemicals made in the United States, because yes, chemicals are important, and we can think of a lot of chemicals as being natural, but a lot of chemicals, once we identified what they were, we figured out ways to manufacture them for commercial use. So we have number 8 is 1,2-dichloroethene, but then we move up to sodium hydroxide, phosphoric acid, which is anhydrous, chlorine, ammonia, propylene, ethene, and then the top one is sulfuric acid. And you can see what the uses of each one is for in the formula. And so, example, the way we read formulas, usually we can, I don't know if we'll have time, but chemists learn how to get to a point where they can see the formula and say the name. But the way we read formula, for example, for sulfuric acid is basically H2SO4. Okay, and in this class, you can talk about things in terms of their formula. If you study hard and get to a point where you can name something based on seeing its formula, that's a good place to be in. All right, we're going to move on to the next section here, and this next section of Chapter 2, we want to look at physical properties and chemical properties of matter, and they're not the same thing. They're actually defined very differently, and so that's important. Be able to classify changes of matter as physical or chemical. Sometimes matter changes and it's a physical change. Sometimes matter changes, it's a chemical change, and there's actually definitions that allow us to classify that appropriately. And look at gas, liquid, and solid states in terms of their particles. Basically, that is know and understand the particle theory of matter. Explain the law of conservation of energy as it applies to changes in matter. Distinguish between a mixture and a pure substance. So, what is matter? Well, we can talk about matter in lots of different ways. One characteristic of matter is that it has volume. Volume is simply defined as the amount of space that something takes up. Here it says the amount of three-dimensional space an object occupies. A chair and a desk cannot occupy the same space at the same time. It's that kind of understanding. Mass is a measure of the amount of matter that makes that thing up. Students very, very frequently get mass and weight confused because they think, well, if I take this substance and I put it on this scale and I try to understand how much is there and I figure out there's 3.2 grams, that's its weight, because we associate scales with weighing ourselves. But that is not what mass is. When you do that on a scale, what you have determined is that there's 3.2 grams of stuff, okay, the amount of matter. And weight is a measurement of force. It's really a measurement of the force of gravity being exerted on anything. So mass is its own thing. And so how do we define matter? Well, we define matter in terms of mass and volume. And basically what we say is matter is anything that has mass and takes up space. Now, the basic building blocks of matter, if it's something that has mass and it takes up space, there must be things that make it up. And we can, just like if I were to ask you what the basic building block of the science building is, you would say cinder blocks or those bricks. Well, we can ask the same thing about any matter, and that brings us to a discussion of the atom. The atom is the smallest unit of an element that maintains the chemical identity of that element. What does that mean? It means you can talk about an atom of gold because that atom of gold has all the same chemical characteristics and features as a nugget of gold. Okay, and When we talk about an element, we're talking about things that exist purely as atoms. And this is where we get into the periodic table of the elements. But to define an element, we say that it's a pure substance that cannot be broken down into simpler, stable substances and is made of one type of atom. So gold is an element because you don't have two different things that come together to make gold. You can split gold down and split it down and split it down to ultimately you get an atom of gold. Not an atom of A and an atom of B that make gold. Okay, that's the definition of an element. And there are lots of things that we probably don't think of as being elements that are silver and carbon and oxygen, but more to the solids and the metals, aluminum, lead. Those types of things are elements. There's not two different things that come together to make it up. Now, from an atom, we go to a compound. And a compound is a substance that can be broken down into simple, stable substances. Each compound is made from the atoms of two or more elements that are chemically bonded. So a compound is defined as being made up of more than one thing. Water is a compound because water is H2O. It's two hydrogen atoms and one oxygen atom. So there you have your two or more elements that are chemically bonded together, and therefore that's a compound. These diagrams here show you different ways to model these atoms in terms of compounds. So you can see in the stick model on the left, you have carbon atoms that bond into other things. In the diagram on the right, you see hydrogen atoms bonded to oxygen atoms bonded to carbon atoms. So this gives you an idea as we structurally model these things what compounds might look like. Now we were going to also look at, we're going to need to understand properties in matter and how those properties change and how we define those changes. There are lots and lots of properties, and the properties can have some kind of dependence on the amount of matter that is present. For example, volume, so the extensive properties as we're defining here have to do with amount. Mass is also another extensive property that has to do with amount. And then the amount of energy in a substance. How much energy does that substance hold? Very often the amount of energy a substance has to do with the bonds, but how many bonds there are. And those are all extensive. We can also look at what we call intensive properties. And these are properties that don't depend on the amount of matter present. So whatever the melting point is, doesn't matter if you've got 10 grams or 1 gram, the melting point will always be the same. What's the boiling point? Same concept. What's the density? And by the way, these never change. Okay, if you're talking about the melting point of gold, it's a known property. It is always the same. There's nothing you can do to gold to change the melting point. What's the boiling point? Okay, the boiling point of water is always 100 degrees Celsius. Let me take that back. We consider that a known given in terms of our understanding of the properties of water, but with certain things, with melting point and boiling point, there is going to be issues of barometric pressure, that changes these things. But generally speaking, these are knowns. Density for certain. Whether or not something can conduct electricity is not necessarily a specific number, although it can be. We're not going to look at it that way. But whether it does or doesn't conduct electricity, that will always be the same, regardless of how much of the substance we're talking about. And then the ability to transfer energy as heat, again, an intensive property. And we have this table here that I'm not going to necessarily go over in great detail because it is in your book. But I will point out, the three on the bottom, index of refraction, that how much light bending happens in a substance as light passes through it. Malleability is the substance's ability to be hammered or beaten into thin sheets, and ductility is the substance's ability to be drawn into a thin wire. And those last two, malleability and ductility, usually end up being properties that are descriptive of metals. Now we can break this down into physical properties as well. and the physical changes that take place. So a physical property is a characteristic that can be observed or measured without changing the identity of the substance. Okay, so when we look at this thing and we look at this aspect of this substance, can we look at it, can we measure it, can we observe it without anything changing? Melting point and boiling point, even though obviously that includes usually the addition of heat or some other contextual change, does not change the substance itself, and therefore it's a physical property. Excuse me. A physical change is a change in a substance that does not involve a change in the identity of the substance. So if the change takes place, but it doesn't change the identity, that's physical. Water is the classic example here because water can freeze, water can melt, water can vaporize, but it's all always still water, and therefore it's considered a physical change. And you see here, grinding and cutting would be a physical change, and melting and boiling, which I've already mentioned. As we continue to talk about this, we can then move this into a discussion of a change of state, and that again brings us to the example I used about water. A change of state is a physical change of a substance from one state to another. Okay, sometimes we use the word states, sometimes we use the word phases of matter, but what are the states of matter? Solid, liquid, gas. These are the ones that everybody knows all the time. We've been learning about solids, liquids, and gases since elementary school. The other one is plasma, which is considered newer. When I was in elementary school, they did not teach about plasma. I don't think when I was in high school they taught about plasma, but we certainly learned about solids, liquids, and gases. And we can talk about each one of these because they are different. Even though the substance itself doesn't change, they are viewed and observed differently. For example, in the solid state, matter has a definite volume and definite shape. That's pretty straightforward. Volume doesn't change in the solid state. This is where you have a cube of sugar, and you can actually calculate the volume by taking measurements. That volume doesn't change, and that shape doesn't change. We also have liquid. Still a definite volume. In terms of a liquid, the volume doesn't change. Okay, if I have 10 liters of water, that's going to be 10 liters of water whether I put it in a mug, in a cup, whether I hold it in my hand. But it will always have a different shape. Shape is indefinite. So that 10 liters of water is going to look different in the mug than it's going to look in the small cup, than it's going to look in my hand. We move on then to gas, and this is where it starts to really get crazy in terms of our understanding of matter, because with gas, there's no definite volume, there's no definite shape. Gas tends to fill the space that it's in. So if you put gas in a sealed 10-liter cylinder, there's 10 liters of gas. If you take that gas and you put it in a sealed 20-liter cylinder, there's 20 liters of gas. If you take that gas and you put it in a sealed 1 liter cylinder, there is 1 liter of gas. So you see the volume is changing here, and obviously with gas, much like a liquid, the shape changes. These could be square cylinders, these could be circular cylinders, these could be triangle. The gas is going to take the shape of what it's in. And then there's plasma. Plasma is a high temperature physical state of matter. Atoms lose most of their electrons, which are the particles that make up atoms. The classic example of plasma is the fluorescent lights. Okay, the electricity is passing through a sealed tube that has a gas in it. Different gases actually give you different colored lights, and this is where we get our neon lights from. And as the electricity passes through, it heats up that gas, it loses its electrons, and it takes on a new phase. It's not a gas at that point, and that's where the classic example of where plasma as the fourth state of matter is found. This diagram here shows us water in the three states as a solid. You see all the water molecules, the H2Os are bonded together. They have a regular repeating pattern, which gives it its crystalline lattice. And as a liquid, notice that they're not all stuck together. They can move around. And then as a gas, certainly they're not even in constant contact with each other. They're bouncing around, filling the space, whatever space they're in. Now, to move from physical properties, we'll talk about chemical properties. And chemical property relates to a substance's ability to undergo changes that transform it into different substances. So here, the fundamental difference between physical and chemical, guys, is that when you start talking about chemical properties, these things are changing into different substances. And therefore, we have to be able to talk about and understand the change that they're undergoing. A change in which one or more substances are converted into different substances is called a chemical change or a chemical reaction. And this is where our chemistry starts to move forward to what we're going to study, and especially the type of stuff we're going to do in the lab. When a substance changes from A to B, it's a different thing than what you started with. That is, by definition, a chemical change, and ultimately, it is a chemical reaction that has taken place. The reactants are the substances that react in the chemical change. So the reactants are the things that you start with. Okay, if I have, let's see, if I have hydrogen and I have oxygen separate from each other, those are the reactants. If I do something or catalyze them so that they bond together and you create water on the other side, now that water is the product. It's the substance that's formed by the chemical change. So hopefully that helps you understand how we define reactants and products. And what we see here is usually reactants are going to be represented on one side of the chemical reaction or the equation, and products are going to be represented on the other side. And another example given here is carbon plus oxygen. Carbon and oxygen by themselves are reactants, but when you put them together, they form carbon dioxide on the other side, which is the product. And then we'll show it like this. Usually the reactants are on one side, they're separate from each other. Usually there's a plus sign that represents they're being put together in a reaction, and then there's a arrow that shows the yield, and on the other side of that arrow is going to be the carbon dioxide or the product. These diagrams show us some examples of chemical changes that take place and the types of things that you can look for to define whether or not something is a chemical change. In A, we've got acetic acid, which is vinegar, sodium hydrogen carbonate, which is baking soda. You mix them together, you get bubbling. That bubbling represents the formation of a gas. Carbon dioxide is forming. That's a chemical change. In B, you have solution of sodium sulfide and cadmium nitrate are mixed. And when you do that, you're literally pouring one clear solution into another. But what happens is you got that yellow cloud, a solid precipitate forms. That is usually evidence that a chemical change has taken place. When you take, in C, when you take aluminum and you put it with iron 3 oxide in the clay pot, you get heat and light is being released. That is usually a sign that a chemical reaction is taking place or a chemical change. And then D, phenolphthalein being added to ammonia that's dissolved in water, you get a color change. You can't see it real well, but the liquid has turned pink, and it goes from colorless to pink, and usually a color change is a sign that a chemical reaction has taken place. Another example of this is electrolysis. I'm hoping that we can do a lab that actually lets us attempt to do electrolysis. But if you take water and you run a cathode and an anode, basically passing electric current through the water, it actually causes the water to break up into its component parts, and you can actually collect oxygen and hydrogen separate. You can test that you've collected oxygen and hydrogen, and that electrolysis, is also representative of a chemical change that has taken place. You don't have water anymore. You have hydrogen and you have oxygen separate from each other. And then to compare physical and chemical properties, we can see the mercury 2 oxide. It's bright red, orange red. It's odorless, crystalline, solid, almost insoluble in water. Chemical properties: it decomposes when exposed to light or at 500 degrees Celsius to form mercury and oxygen gas. On the right there, physical properties of oxygen. It's colorless, it's odorless gas, it's soluble in water, but it supports combustion, which is a chemical property. And then you get the mercury, as this has been separated out. Mercury silver white liquid. It's a liquid metal at room temperature. When it is in the solid state, it's ductile and malleable. It can be cut with a knife. It's a soft metal. But as a chemical property, it forms alloys with most metals except iron, combines with sulfur at room temperature, reacts with nitric acid and hot sulfuric acid. So that, just looking at everything that's happening in there in that test tube, and this gives you the opportunity and the exercise to try to make sure you understand physical properties, chemical properties, physical changes, and chemical changes. Now, with these changes in matter, our laws in science mean that we also have to understand that this affects energy. And energy is always involved when physical or chemical changes occur. So none of this stuff that we've talked about happens in a vacuum. And what I mean by that is none of this happens without energy being affected in some way. And the first thing we need to understand about energy is that it can take various forms. Certainly, energy can take the form of heat. It can take the form of light, okay? And it can be absorbed or released in a change. What we have to remember in terms of the laws of thermodynamics, we're not going to go into this in great detail, but energy is never destroyed or created. It's always moving around, okay? And we can actually show this mathematically and understand this mathematically. But that's very important for you guys to understand. It's never destroyed. It's never created. That is the law of conservation of energy. And so how we classify matter, we start at the top. Here's a wonderful model as a flow chart. You have matter. The first question you ask is, can it be separated? Well, yes, it can. So then it's a mixture, okay? Now, is that mixture uniform? If it is, then it's a homogeneous mixture. Example would be air or sugar and water or stainless steel. If it's not uniform, then an example would be that it's a heterogeneous mixture. That would be granite, wood, or blood. You can physically separate blood into its parts. But if we go back to matter and we ask the question again, can it be separated? We say no, then it is a pure substance. And the next question we ask is, can it be decomposed by ordinary chemical means? If the answer is yes, then it's a compound. Water can be decomposed by normal, ordinary chemical means. Sodium chloride, that's salt. Sucrose, that's sugar. If the answer is no, then that's where now we know we have an element. It's gold, it's aluminum, it's oxygen and chlorine. This flow chart is very basic, but it's important to at least some of our understanding of what we do in chemistry, because we can start with an unknown substance of matter and we can ask these questions experimentally and very quickly work down to classify the matter, and ultimately, because of what we know, ultimately be able to identify specifically what the unknown substance is. This just shows exactly what we talked about in terms of pure substances, mixtures and compounds versus elements, and homogeneous mixtures versus heterogeneous mixtures. So let's talk about this classification. Let's talk about mixtures, because a lot of our labs the first week or so are going to deal with this. By definition, a mixture is a blend of two or more kinds of matter, each of which retains its own identity and properties. So you have two or more things, but they retain their own identities and properties even though they're mixed together. So that means they're mixed together physically, not chemically. And because they're mixed together physically, they can usually be separated. And what I mean by separated is separated by physical means. Okay? Homogeneous mixtures are called solutions. So I want you to note here, guys, that even though solutions are a particular kind of mixture, they're still mixtures, which means it's physical, and it means that they can be separated by physical means. Okay, they're uniform in composition. Saltwater solution is homogeneous. You can take a drop of salt water, put it under the microscope, and you're not going to see component salt in water. Okay, that's what we mean by uniform. That's what we mean by solution. But I want to add this, you can still separate salt water physically. So it's still a physical component. Heterogeneous mixture is different. It's not uniform throughout. Clay and water mixture. a clay and water mixture is going to look completely differently to the naked eye and under the microscope as a saltwater solution will look. So this picture shows you exactly what we're talking about. In the beaker on the left, it's actually a sugar water solution, and the beaker on the right, it is clay and water. Silicon dioxide is going to be clay molecules. Pure substances have a fixed composition. We already saw this in the flow chart, so I'm not going to spend a tremendous amount of time on this. Pure substances are either compounds or they are elements, and they differ from a mixture in certain ways. Every sample of a given pure substance has exactly the same characteristics and properties. So if it's a pure substance, every time you get a different sample, it's going to be exactly the same. What do we mean by composition? Water is always 11.2% hydrogen, 88.8% oxygen by mass. That's what we mean by same composition. Any water you get anywhere, we know it's a pure substance because when you do the math, if you test that sample, it will always have that composition. So, homogeneous examples: iced tea, stainless steel, maple syrup. Heterogeneous: orange juice, tomato juice, chocolate chip pecan cookie, granite, salad. Okay, this is your table that lays out the basics of different mixtures. Now, this takes us into a section where we want to look at the elements in more detail and start to understand the periodic table, understanding symbols of elements and their names, understand the arrangement of the periodic table, and list the characteristics that distinguish metals, nonmetals, and metalloids. So we have our introduction to the periodic table. You have a modern name, you have a symbol, and you have an older name. I'm not interested in the older names. I am interested in you memorizing the symbols and memorizing the names that go with the symbols. Sometimes this is easy. Okay. For example, actually none of the easy ones are here, but what it will show you is the ones where it's harder. Okay. Why is gold AU? Carbon is a capital C. Gold is a capital A, lowercase u. Oxygen is a capital O. Right? Hydrogen is a capital H. Helium is a capital H, lowercase e. Those make sense. Why is potassium a capital K? Why is mercury a capital H, lowercase g? This is because some of these, their symbols were based on the older names. So notice copper is capital C, lowercase u. Well, that's because the older name of copper was cuprum. Okay, so some of these you're just going to have to memorize. This shows the regions of the periodic table, the metals, the metalloids, the nonmetals, and the noble gases. The vertical columns we call groups or families, and that's important because everything in a group or a family has very similar properties. Okay, at least similar chemical properties. The horizontal rows are called the periods. Okay, and those are important too, not because of similar chemical properties, but because things change pretty regularly across the period, and you'll understand why as we talk more about this. Metals, metals generally are good conductors of electricity and good conductors of heat. Most metals are solids at room temperature. Not all of them, but most are solids at room temperature. Most are malleable. We've already talked about this. Most are ductile, and we've talked about that. And they conduct electricity and heat well. Examples would be gold, copper, and aluminum, which you see here. Then there are nonmetals. Nonmetals are poor conductors of heat and electricity. Many nonmetals are gases at normal room temperatures. They are brittle if they are solids. They do not conduct heat and electricity well. And then you see pictures here of pretty common nonmetals: carbon, sulfur, phosphorus, and iodine. Metalloids, and you have to go back to your periodic table to see where these are. These are elements that kind of fall right in the border, right in the gray area. They have some metal characteristics and they have some non-metal characteristics. They're all solids at room temperature. They are semiconductors of electricity, which means they aren't as good as some metals, but they're better than nonmetals. The noble gases, you'll find these on your periodic table in group 18. Noble gases, one of the reasons they're called noble is because they're unreactive, generally speaking. At room temperature, they are gases. And that ends everything for Chapter 1. So what we'll be doing now is you guys in class will be getting a lecture on your lab work for the week. You'll spend most of your time in class working on your labs, as this has already been explained. We also are planning on doing Chapter 2 this week as well. And you should expect your quizzes on Thursday. And you should expect your Chapter 1 and 2 test on Friday. Please let me know in class, obviously, if you have any questions.